And then other folks will join as we get started. So I hope you all had a good and a safe weekend. It's been kind of crazy. Few things. I'm going to go and do some class business at the very beginning. I've got PowerPoint to go through and show you. But per the email that I sent out earlier today, one thing you want to remember is we have our test, our first test on Thursday. I created a new homework assignment, and the main reason for doing that is so that you get practice in the material that we're currently doing. I found that if I don't create a homework assignment, it doesn't get a lot of practice. So, you know, I want to make sure you guys have that. So you have the extra credit as well. And then, so today is the last day of new content. It actually should be a relatively quick day. The content for this is pretty straightforward. Now, equilibrium is one of our biggest topics in second semester Gen Chem. It undoes a lot of the things that you kind of learned in first semester Gen Chem, but it reframes it in a way that I think is actually something that's really good to think about as you go on and be future scientists and engineers. So that's all kind of what we're going through today. At the end of today, we'll be done with new content. No content beyond this portion of Chapter 16 Pro will be on the second exam. I want to reserve Wednesday for review because from solutions to kinetics to equilibrium, we've actually covered like a really broad range of stuff. And I want to make sure that we've got time to feel that we're confident in that. So that's why I don't want new content for Wednesday when we get together. So again, in the email, what I suggested is if you have questions like specific ones, which would be a really good idea, send them to me so that I can start to work them out on pen and paper and show you some of the methods that I use to work through problems like that. We can put them together on Wednesday. So between now and then, please make sure you're doing lots of problems. Work on exam 1 prep. That's the one that's in mastering. And then also the exam 1 study sheet that I sent out is a good thing to go from as well, so that you get lots of chances to look at lots of different kinds of problems. Okay. All right, so we've got a good number of people here. So I'm going to go into our, the PowerPoint that I've got for today. And there's not a ton of us here, so if you have a question at any time, feel free to unmute and ask it. You can ask it in the chat as well. I'll take little breaks throughout so that I can answer questions. I've also created a small problem set in mastering for some in-class work, so there'll be some breaks that we take. All right, so let me get the laser pointer here. So today's class is 120. Some class updates to go into. We're going to define what equilibrium is. Let's see this. And we're also going to calculate the equilibrium concentrations as well. So we're going to do some concentration with that. All right, good. So let's go on from here. So as far as class updates are concerned, if you're paying attention to your grade, extra credit 1 and 2 are done, quiz 1 and 2 are done, homework 1 and 2 are done. The only issue is that extra credit 1, for some reason, is not appearing in the gradebook. There's some problem that I haven't been able to get to the bottom of, but it will be in there. Your work will be credited to you. So don't worry about that. It will appear in there. Just give me a little minute to get whatever the issue is solved. And that will be there. Now, you also might notice that you have fewer points than what is potentially available to you right now, and that's because the lowest of everything you submit from the day class started till now has been dropped. And so you have 2 quizzes, but only one of them counts so far. Next week, you'll have 3 homeworks, and only 2 of them will be in there because one of them is your lowest. All right, you've got a new homework. It's homework 3. It's due Sunday. You have new extra credit. Extra credit 3. It's due Friday, and then the exam prep that I talked about previously. Our first exam is going to be Thursday, the 4th, from 12:01 a.m. to 11:59 p.m. That's the window you have to complete the test. We will not be using honor lock. I described that very early on in the semester, and my reasons for doing so are stated earlier in the semester. But there are two distinct sections that you're going to have to complete for this test. And the reason I do that is because I can't mix the way that things are graded in one individual section, so I needed to split it up into two. So the multiple choice section will be one of them, will be between 8 and 10 questions. And for each of those 10 questions, 8 to 10 questions, you will get one chance to answer it. So if there are 4 possible answers and you select C, the computer's going to say, okay, thanks, and then move on, whether or not C is the correct answer. So you'll get, it's basically, you get it or you don't kind of question. The numerical answers are a little different. Those have between 8 and 10 questions, and they're going to require some kind of input. So you have to like type in a number or maybe write in a response. So those questions, you will have more than one opportunity to submit the answer. If you put it in and it's incorrect, the computer will say try again, or incorrect with a red X, and you get an opportunity to try again. Now, on your next try, the total point value you can get will be a little bit lower than you would on your first try. And then after that second try, that's the last of the submissions that you can do for any given question. So you get up to 2 tries on any one question. This will be timed. So you have so much time to complete the numerical, you have so much time to complete the multiple choice. I'll arrive at those times when I put all this together later this week. And the total number of points that will be available for this exam is 100, and that'll go to your grade. And it'll be very quickly the biggest thing in your grade. So this is going to drive your grade more than anything else so far. Okay. And if you unmute, if you want to unmute and ask me questions on the test before I dive into stuff for today. Any questions on this stuff before I move on? No? All right, let's move on to equilibrium. So it starts the 16th chapter. It talks about fetal hemoglobin, which is actually a really cool concept. The idea between equilibrium is that this is a state that every system, chemical systems that we're interested in, but other systems as well, wants to arrive at. All the energy in the world is forcing any particular chemical system to arrive at equilibrium. It's a dynamic state. And at that dynamic state, there are 2 reactions, a forward reaction and a reverse reaction, and the rates for those reactions are equal at equilibrium. So if you consider H2 plus I2 going to 2HI, there's a forward rate. Now, again, looking at the equation, I don't know what the rate law is. So I'm just writing it as KH2 to the X, I2 to the Y. And then there's a reverse reaction of this K times the concentration of this, turning back into H2 into I2. And at equilibrium, these 2 rates are equal to each other. So we have a reaction going towards HI and a reaction going towards H2 and I2. And the rates of those reactions are equal to each other. So that is what equilibrium is. That is its definition. Now, it's all a lie. Now, there's no lie about what the definition of equilibrium is, but when we talked about chemical reactions in the first semester, you always saw us going, A plus B goes to C. Reactants go to products. And we always treated it like it's a one-way street. Everything on the left becomes everything on the right. That is simply not the case. So all reactions that you've seen in first semester should actually be equilibrium arrows if we're really telling the truth about stuff. And it just might be that equilibrium is very far to the right or very far. We'll talk about what that means as it comes up. But all reactions proceed towards an equilibrium. And once they get to equilibrium, they tend not to leave it. So they tend to stay there unless it's disturbed. So if you heat something, add more of something, agitate it in some way, it will stay in equilibrium until it's disturbed. So this is a really good graphic for this. At time 0, there are H2 and I2 molecules. The H2 are the little white ones, the little purple ones are the I2. And then as the reaction proceeds, some of the I2 and some of the H2 break up and start to form HI. And that continues to happen until you're at this sort of 4th time period here, where we don't seem to be making any more HI. So the rate at which this is HI breaks up to make H2 and I2 is equal to the rate at which H2 and I2 are forming HI. So there's no net change in the concentration of any of these things once equilibrium has been established. So we've got some amount of H2, and it's going down as a function of time until it flattens out, which means that its concentration is not changing with respect to time. I2, same thing, goes down and then flattens out here. And then HI, it goes up quite a bit quickly at first and then flattens out. So at equilibrium, there's a concentration of HI, a concentration of H2, a concentration of I2. That means that all three things are present at equilibrium, right? But they're not necessarily present at the same amount. We'll go over the amounts in which things may be present at equilibrium, but these represent what's going on in equilibrium. So we still have these reactions happening, but there's no net change. And your book uses, like, there's lots of different analogies. I've used the bridges between St. Pete and Tampa, but this is a really good one as well. So if you imagine two different countries separated by a border, and initially there's no inhabitants in country B, lots of inhabitants in country A, and there's this border. So that's at time 0. Now when you open up the door, some people from A will start moving over to B, and over time there'll be flow back and forth across this border, A into B and then B into A. And the rates of change from both of those are equal. That's equilibrium. But the important thing to note is that we do not have to have an equal number of people on both sides in order for equilibrium to exist. It just means equal movement. Okay, so basically at that point it's sort of 1 in, 1 out. So we don't need equal numbers. Excuse me, that's a very important point. So please keep that in mind. At equilibrium, the number of things on both sides of this border are not necessarily equal. They can be, but they are not necessarily equal. And so we represent this as a ratio. We call it an equilibrium expression. You guys are going to become familiar with this as a K constant. K is going to be used a lot throughout this entire semester, and this capital K represents an equilibrium expression. So here's a general reaction. A moles of A plus B moles of B goes to C moles of C plus D moles of D. We write an equilibrium expression as the concentration of our products divided by the concentration of our reactants. So whatever is here on the right-hand side divided by whatever is on the left-hand side. That's how we end up writing an equilibrium expression. And when we do this, the concentration, here in brackets, so that's how we show concentration. The coefficients for this, whatever they are, 0, 1, 2, 3, usually 1, 0, 1, 2, 3, becomes in the exponent here. So C moles of C here gets represented as concentration of C raised to the C power. So whatever this number is becomes that number. Whatever this number is becomes this number. Same thing for the things on the reactants. So with a real system, H2 plus Br2 goes to 2HBr. At equilibrium, the equilibrium expression right here is written as the products, HBr, squared, because that's the coefficient, divided by the products, H2 and Br2. There are no coefficients in front. They're taken to be 1 apiece. As a result, H2 and Br2 are the numbers that we have down here. This particular system has a very large value of K, 1.19 times 10 to the 19. So what must that mean? Well, if you have a large value of K, just looking at it as a ratio, it must mean that your numerator is very big and your denominator is very small. That is the only way in which we get a number that is greater than 1. And this is a number that is much greater than 1, which means that at equilibrium, there's a lot of this stuff around, a lot of products, and not very many reactants. And the way we talk about this is we say that the products are favored at equilibrium. So we have equilibrium that is more of this stuff than this stuff. Excuse me. Same exact thing. Here's the general reaction: A moles of A, B moles of B. Same stuff from the last slide. But here I've got N2 plus O2 going to 2NO. This is different reactions that have a different reaction, equilibrium constant. The It turns out that this is a very small number, 10 to the minus 31 at 25 degrees Celsius, which means that when equilibrium is reached, there's not a lot of product. Our numerator is very small, our denominator is very large. So a small k means that we have way more reactants at equilibrium than we do product. So this side of the equation is the one that's favored in equilibrium. This side is not favored. We don't have as much. And that's fine. That can happen for lots of different thermodynamic and kinetic reasons. Not necessarily a good or a bad thing. So there's a significance to this stuff. I'm just showing you the same two things we had before. When it's a large number at equilibrium, here's our expression. This side of the equation is what's favored. When it's a small number, the reactant side of our equation is what's favored. Okay. So let me, I'm going to stop sharing there. And I'm going to bring up a class set of problems that I was working on, so that you guys have some practice and you get an opportunity to answer the questions. But it looks like I closed it. So while I'm doing that, do you guys have any questions over anything that you saw?
Nope, reading definitely helps.
Okay, good. All right, then let me open up the thing that I made for you guys today for the in-class. This is in Mastering Chemistry, by the way, so if you have access to it on your computer, you can just go in and open it up. I have the same access you do. So we can go through and see some of these things. Come on now. Okay. All right, so go back here to sharing my desktop. Sharing. So you guys hopefully are seeing the thing that says exercise 16.24. That's just starting green by me. So all right. So this says that ethene, C2H4, can be halogenated by this reaction. This stuff plus X2 goes to CH2, C2H4X, meaning that we add a couple of things to this molecule. X2 can be either chlorine, Cl2, Br2, or I2. So there are three figures that they want us to look at and determine what is the largest value of K based on these three figures. Okay, so the figure that they're referring to is sort of down here in the bottom left. And what you'd be looking for are, here's basically our, this is what our product looks like, this thing with the little green, a bunch of white around it. This is what one of our reactants looks like, Cl2, and then this is what one of our other reactants looks like. So what you can see here is there's just two of our reactants, one molecule and another molecule for one of them, and one molecule and another molecule for another. So there's a lot of product here, not a lot of reactant. So that would tell me that this has a relatively large, I've got more product than reactants at equilibrium, so that's probably that's on the large side. If I click over here to this one, now I've got 1, 2, 3, 4 of my molecules present, of my reactant molecules present, and not as much as this one. So this one has a smaller value.
Professor, I think you might have muted yourself accidentally, or maybe my headset just went out.
No, I'm not muted. Anyone else hear me?
For some reason I can't hear anything. Huh.
I can hear you.
Okay, you can hear me, so I think I'm not muted, so that's good news. Not muted. Okay, third one, if I'm taking a look at this, I've got 1, 2, 3, 4, 5, 6, 7 of my reactant molecules still there. Only a couple of my products there, so that means that this K value would probably be of the smallest. So this is all pictographically. So here I've got a lot of products, fewer products, not many products at all. So this would mean I have the largest K value, middle K value, and then the smallest. See if that's right. Green check mark of happiness. You can actually go through and put the numbers to it if you want. That is totally fine, but it's also something you can do to the picture. Okay. All right, so there's another question. We're going to get to that one in a minute. So stop my share. There. And start sharing the PowerPoint. Okay. So let's say we want to change the reaction. Is there any sort of effect on the equilibrium? So we used to say there's like a reaction going forward and a reaction going backward. Well, if that's the case, then what are the products and what are the reactants? Really, if this is an equilibrium, these two things are the reactants of this product, but if I decided to write it first, this is the reactant that makes these two products. And it's the same system. They're on opposite sides of the earth. So referring to one as products and the other as reactants sometimes can lose a little meaning without a K value. So written this way, I've got my products up here, 3C. And so when I write the K expression, it's C raised to the third, and on bottom we've got 1A, so it's A with no exponent, and I've got B, an exponent of 2, so I've got 2 B's. So that's my K expression here. Now, if I decide to write this where this is written as 3C goes to A plus 2B, then these guys are the ones that don't. And C is the one that goes on bottom. It should look like this. So when I reverse the chemical equation, that is, write the products as reactants, products, what that means is that I'm inverting the K value. So K of the reverse reaction is 1 over K of the forward reaction, K of the forward reaction, raised to the power of 1. Okay? And this F and this R, they just mean forward and reverse. They're there for labeling purposes only. The number that's associated. So if this number, let's say this KF value is larger than 1, because that equilibrium without a lot of this, that means that when I reverse it, this will be smaller. The inverse of that number will be a smaller. Let's say I'm going to multiply this reaction. So we've had to do that for Hess's law or some other things like that, where we multiply everything by a certain number. So here's my fourth general reaction. A plus 2B goes to 3C. That's its equation. And then I'm going to multiply that by some number n. It could be 1, 2, 3, 4, whatever. When I do that, this becomes the number of moles. So that becomes my exponential. And there's already a 2 here, so 2 times that number becomes my exponential. So 2n. 3 times that number, 3n becomes my exponential there. And so whatever number I multiply this by, that number becomes the exponent for all of these things. They're a thing you multiply the exponents by. Which means that this is my fourth reaction, and I'm going to go through and multiply it by something. Now it's raised to some n1. Okay. And then finally, if I have 2 separate reactions and I want to add them together, we were doing this with mechanisms last time. So I've got A and 2B, and the 2B goes on to become 3C. So my K expression for the first one is B squared over A. My equilibrium expression for my second one is 3 cubed over B squared. That part is all relatively straightforward. Now, if I combine them, add A and 2B, they become my product, my reactants, and then 2B and 3C become my products. I got 2B on both sides, so it gets loud. So A going to 3C is my net reaction. In this case, 2B would be like 2B. So this is my new expression for what's not crossed out. If I had left what was crossed out in there, it would look like this. C squared from this side and then B squared on bottom here. So both of those would be there, but they cancel out. So my combined K is equal to the individual Ks that I have in reactions. Here, those B's end up canceling. That's the product. Let me escape there. I'm going to stop my share. And then there's a question we can do that is based on that. Share the screen again. You guys see this? Considering the following reactions?
Yes.
Good. So, forget that it says KP. That's not important to us right now. And someone's the door. Excuse me 1 second, okay? Okay, sorry about that. Kid's dead. All right. So we've got these two reactions here. NO plus half a mole of Br2 goes to make NOBr. That's its K. Forget the fact that it says Kp. We'll go over Kp's and Kc's in a second. It doesn't have a bearing. Now you have this other reaction. 2NO is in equilibrium with nitrogen and oxygen, and its Kp is 2.1 times 10 to the 30th. So how can we combine these two reactions to make this third one, this bottom? So you either have to multiply them by some number, reverse them, and definitely add them together. So the way we look at this is, see how we've got N2 on this one right here as a product? Well, here N2 is a reactant. So we're definitely going to have to turn this one around. So it's going to end up being O2 plus N2 back and forth to make 2NO. All right, good. Now, this one right here, I've got NO on this side, half a mole of Br on this side, and NOBr on this side. I should have 2 NOs and 2 NOBRs. So if I'm going to put these together, I'm going to need to multiply that one by 2. 2NO plus Br2 goes back and forth to make 2 NOBr. And when I add these together, I'll get O2 plus N2 plus Br2 back and forth to make 2 NOBr. And that's the reaction I'm looking for. So we add these two together after this one's been reversed and after the top one has been multiplied by 2. So to reverse that one, it's going to be 1 over 2.1 times 10 to the 30. And then this one, we multiplied it by 2, so this number gets squared. Times 5.3 squared. So let's see what we get. Two significant figures, 1.3 times 10 caret minus 20. Yay, correct. Okay, and you can see all the work we had to do there. We just had to multiply the top reaction by 2, reverse the bottom reaction, and then our K becomes the product of those two things. So 5.3 squared times 1 over 2.1 times 10 to the 30th gives us a very small number, which means that at equilibrium, the reactant side of this got a lot more of that stuff than we do the product side. Okay. Right. Let me see the next simplify back to the I'm going to do that with the soft share. And remove share. Live share. So all of the equilibrium expressions we've been doing so far have been in units of, well, not in units, but have been sort of, we looked at them in terms of concentration of reactants. So the equilibrium expression for the music concentration looks just like all the ones we've seen before. You should be able to write these equilibrium expressions. But what if I only had pressure information? Usually I have concentration information if I have something that gets me moles and a unit of volume. I have pressure differential. I just have partial pressures in terms of atmospheric pressure. So if I knew the partial pressure of each of these in atmospheres at equilibrium, then I have to repeat. Kc and Kp are not necessarily the same. They can, but they are not necessarily the same. There's a relationship too. So here's our general reaction. A moles of A plus B moles of B goes to C moles of C. Delta N is the moles of my product using the final reaction. Okay, so just remember, for ideal gas law, the ideal gas law does not care about the identity of the gas. Just how many moles there are. These coefficients in front tell me how many moles of gas in a particular reaction. So the sum of my two coefficients on the right-hand side minus the sum of the coefficients on the left-hand side is this thing called delta. The relationship between the two is like this. Kp is equal to Kc, the quantity RT raised to the delta n. Okay, where the delta n is the difference between these two numbers. Now, what I had said previously was that if these aren't necessarily the same. However, they can be the same if we have the same number of moles on both sides of the equation. So if I had 2 moles on this side, 2 moles on that side, that's 0. RT raised to the 0 is 1. Kp equal to Kc. If that's the case, then they can be equal. If that is not the case, they are not equal by some exponent of RT. So that is something you want to be cognizant of. One of the things you would be asked to do in the homework is to convert between Kc and Kp. Another thing about this is we do called heterogeneous equilibrium, meaning that we can have reactions that involve different phases of matter. So here's one where I've got carbon dioxide and water, and they combine to make hydrogen and bicarbonate acid. This is the vinegar and baking soda. And so when I write the equilibrium expression for it, you might notice that something is missing. Here are my two reactants, they're on top. Here are my two products, on the bottom. This H2O liquid, here liquids do not appear in the K value. The next slide will kind of give you a reason as to why. For solids, it's the same thing. Solids do not appear in the K constant. So here I've got my two products, CO2 and C, but with CO2 in my product, and CO here. Pure solids do not appear in the K number. We just leave them out. They don't go in there. The reason they don't go in there is because if I had more solid but less solid in here, it does not change its concentration. The concentration of a solid is really its density, the ratio of mass to solid, grams to volume. Okay? Same thing with pure liquids. Its density, its mass divided by its volume. You can actually, if you want, calculate the volume of pure water just from its density. And I want to say it's like 44 moles. At any rate, do that in calculations. Having more of this carbon solid or less of it does not change the amount of CO2 and CO that is in here. So changing this does nothing to change the K value, so therefore it is ignored. The K value is basically doesn't affect it. Part of the reaction, but it does not change the order of other stuff. Now, we should be able to calculate K from equilibrium concentrations. So here is a reaction, H2 plus I2 is taken to HI, and this is at 445 cells. One thing I'd like to say about this is that equilibrium constants change as a function of temperature. We're going to get to the math for that later. But your book will often give you this at a particular temperature. There's nothing you need to do with that number right now, except for just sort of mentally log that, K seems to be high when this number is high, this is low when this number is low. One thing to notice, but nothing you have to do with it. So these are my initial concentrations. I'm starting this reaction with a little bit of H2, 5 molar, a little bit of I2, 0.5 molar, and no HI. That makes that a little bit. And when I get to equilibrium, this is how much stuff there is. And so when I do my equilibrium concentration calculation, I get 50. 7/8 squared divided by 1 divided by. If I start this with just HI, reaction kind of goes in this direction. I get a little bit of H2, a little bit of I2, and I have some remaining HI. My K is still 2. This will not change. It's the equilibrium constant. It's what the reaction goes towards. And I actually think this is a really good table for illustrating that. No matter how much of these things that I start with, as long as it's a spontaneous reaction that goes towards its own equilibrium, I'll always end up with the same ratio of stuff. Okay. So this is a really good thing. Now, how we get from here to here is what we're going to get into next. And this is sort of representing the cutoff. Now, the next slide we're going to use for the next test as well. But after 16.6, the math gets a little bit more challenging. So we're not doing that in this test. We're going to put that in with the next test where it's going to go with a whole lot of other math that's just like it. So we're putting that off to the side. Now, we'll go into the next slide because it's the last one, and then we'll do a couple of problems that deal with this. So we should be able to make what's known as an ICE table. An ICE table stands for initial change in equilibrium. So going back to this thing here, here's my initial amount, here's my equilibrium amount. If I started with 0.5 molar of this and I ended with 0.11 molar of this, my change is 0.39 molar. It's the difference between these numbers. Okay. I should be able to put that into a table format and use that to calculate this decay. My question here in the chat. Quick question from Curlis. The rest of the chapter after 16 is next week's content. Yes, that'll be next week. All right, so I got a reaction here. It's balanced CO. So CO plus 2H2 goes to CH0OH. So I've got a reaction that's starting with 0.27 molar and 0.49 molar after H2. At equilibrium, I've got this much CH3OH. What is my K? All right, well, I know how much of this I have at equilibrium. I don't know how much of these things I have. So let's figure it out. So here's my little ICE table. And I'll do some more videos on this for this weekend, for next. But I'm starting with this much CO, this much H2, and no methanol. At the end of the reaction, I've got this much. Things change. So according to my little stoichiometry here, 1 mole of this goes away to make this. 2 moles of this goes away. And 1 mole of this one. Okay, so minus X of this goes away. I don't know how much one will go. Minus 2 times X of this goes away. And X of this forms. Okay, so those are my numbers right here. Now luckily 0 plus X is 0.11. And that tells me that my X must be 0.11. So I can plug in 0.11 for X. So 0.27 minus 0.11 is 0.16. 0.49 minus 2 times 0.11 is 0.27. And I get it. So now I know my equilibrium concentrations of methanol, H2CO. And when I plug that in and try and figure out my K, 0.11 on top, 0.16 on the bottom, and 0.027 divided squared, because it's 2 there here. That equals 9. Okay. So this is my equilibrium expression. Now you might, yeah, that's exactly what I'm looking for. So that's an example of how we would use this in a problem. Now let's stop the share here and go into an actual problem from Master of Chemistry that deals with this. I think we have time for 2 problems. So do you see something here that says, consider the following reaction, NH4HS solid?
Yep.
Okay, cool. So an equilibrium mixture of this has these concentrations, 0.27 molar of this and 0.355 molar of this. They want to know what the Kc is. Well, these are my equilibrium expressions, or my equilibrium amounts. So I don't really need an ICE table. Can I write a K expression for this? NH4HS is a pure solid. How is it? It just is. The same way that NaCl is a pure solid. So that's a pure solid. This will not be an our K expression. So our K expression will just be NH3 times H2S. So the way we solve this is really this number There are no exponents to consider here. 27 times 0.355. And once it's three significant figures, so 0.0959. Yeah. Also, we should notice that this is a unitless number. There is some significance for that, none that's really important for what we're doing. So we're going to wait for mastering to think about giving us this problem. This will be the last one that we do. SO2Cl plus SO2 and Cl2. This is the Kp for it. In a reaction at equilibrium, the partial pressure of SO2 is 0.1344, and the pressure of Cl2 is 0.346 torr. What is the partial pressure of SO2? I wonder if I can do. You guys see like a text box here?
Yes, I can see that text box.
Okay,
Yep.
cool. Thank you. So
That's groovy.
Kp is equal to.
Remember that.
So Kp is equal to SO2 times Cl2. That whole thing divided by So that is my, and there are no exponents in here, so I don't have to worry about this. The other thing I need to realize is that this is all in. So all I really need to do is kind of plug in the things I know and solve for the things I don't know. So 2.91 E times 10 to the third. That's equal to, this is given to me in torr. So I need to know it in ATM. So 0.134 divided by 760. That's how I get that in ATM. Is that right? So that number times my other number, 0.346 divided by 760. And that entire quantity is divided by x. X is going to be whatever this is. Okay. So just rearranging it, that's going to be 2.91 times 10 to the third times x. So basically it's going to work out like this. When I put this in my calculator, 0.134 over 760 times 0.346 over 760 divided by 2.91 10 to the third. I get 2.758 times 10 minus 11. There are 760 torr per ATM. All right. 2.758 times 10 to the 11. And that's X ATM. Okay. I need to multiply that by 760. To get myself the torr. So multiply that number by 760 to get torr, and I get 2.09 or 2.10 times 10 to the minus 2.10 times 10. Yeah. There we go. 2.10 times 10 raised to more time trying to type it than I did trying to solve it. There's one more problem in this set that I'm going to leave to you guys to try on your own. So do try that. These questions are really good at helping you build some of the skills that you need there. Are there any questions that are listed that you'd like answered before we go? Oh, Corliss had one question here. So is any solid a pure solid? And the answer is yes. If you have a solid in a reaction, as long as there's like the little parentheses S there, that does not belong in the K expression. So it is considered a solid, pure solid. Okay. All right. So I will see you guys on Wednesday. We've got, and please do think of problems you want to see done by Wednesday and email them to me so that we can go through and do that. Phil, it's the same question you had. Is it the same for liquids? Yes. Any pure liquid is not any liquid. Okay. I will see you guys on Wednesday. Have a good afternoon. Okay. All right. I'll stop the recording.